anyways, welcome to our first stream in the series on general relativity. So let's see here. We have GR part 1, and this is SR, special relativity, and flat space-time, which we're going to have
Step
a bunch
1.
of these.
A tensor is a thing that transforms like a tensor.
Very good, Sparks. Okay, now, let's talk about what general relativity is. I like Sean Carroll's book. I have not spent a ton of time in it, but I would like to, and that's what this course is going to be about. It's a great book, and the little bit of time I have spent in it, I spent a few days like rummaging through it for stuff. I've liked everything that I've read so far, and I'm looking forward to diving in more. Now, he starts off with kind of like a quote, and I really liked this idea. And I'll read the quote from you. This is from him. It's not a quote from someone else. This is his words. What we experience as gravity is a manifestation of the curvature of space-time. And I really liked that. And let's kind of like unpack that a little bit so we actually know what we're doing, okay? Because we want to like really have a good grasp of what we're trying to accomplish here. So let's start with the previous theory of gravity, the theory pre-Einstein, pre-general relativity. Let's talk about what that is. So we have this inverse square law, which kind of rules everything, right? F equals minus G, big M, little m over R squared. And then there's some unit vector of R, right? And it's just, here we are, we're already off the bat. We see, this is the one you learn in every introductory physics class. It's some force is equal to the constant of gravitation, the two masses, and then over R squared. Now, we can generalize this, like we do, to what? Well, to a force. This is technically a force, right? And we know that we have, that this is also a force, so we can kind of get like some idea of what acceleration looks like in terms of force. So we've done quantum field theory, and now we're doing general relativity. Next series is to unify the two, right? You guessed it, Sparks. Definitely, we're gonna do it as a stream. So here we have forces, and that's all good. Forces. I don't know what this is. Forces! For the fourth time. For the fourthest time. Now, this version of gravity is non-relativistic. And what Einstein did was he took this and he made it relativistic. So that's going to be a lot of what we do today, but we don't need a relativistic form of gravity for everything, right? Everything falls at 2.8 meters squared per second, right? Gravity is not a force. It's 9.81 meters per second squared. Gravity is not a force. Ooh, here we go. So we can talk about gravity as a force, right? And we can show, but you're right, gravity is not technically a force. But we'll get into that in a second. For now, we can talk about what is good about this gravity, this non-relativistic gravity. What can we do? Well, we can do all sorts of types of physics, right? And let me just give you one example. We can talk about the internal structure. Internal structure of sun, right? Of the sun. It doesn't become an issue until this only changes, i.e. we only need relativistic gravity when, I don't want to write, okay, when, what do we have here? When the constant, the gravitational constant times the mass is roughly equal to r, the radius of the sun, times the speed of light squared. That is when we start to worry about needing relativistic gravity. And this is just cool. There's some other things in Hartle if you're interested about when we have gravity, when it's important to switch into relativistic gravity versus non-relativistic gravity. We can do a lot of good things with non-relativistic gravity. And then also we can talk about potential, right? There's another form of this, potential. And potential is potential energy, right? And we can relate this potential to some mass density. So let's relate potential, and this is again non-relativistic, relate potential to mass density rho, right? And we use Poisson's equation, and before I get yelled at for mispronunciation and then I spell it wrong. Ooh, Poisson. Poisson's equation. Poisson. Let's just set everything equal to 1 and do it old school, right? Let's see. And Poisson's equation is the second gradient of the potential is equal to 4 pi g times rho. So we know that there's all types of relationships between this Newtonian version of gravity and the Einstein relation of gravity. But the difference is like sometimes we need more involvement. We need to get into like, we need to understand how things work relativistically. Let me see if there's any other way to cast this that I missed. I don't think so. Pretty sure that's straightforward. Yeah, I can't seem to find it right now. But, and then we can also write this in some form of acceleration. Oops, the sigma. The acceleration is equal to then the negative gradient of this potential. So we can talk about this perfectly fine non-relativistic form. Hey, Zoiku, welcome in. Okay, so now we have our two different Newton's gravities. So these are Newton's gravities. Newton's gravity. It's okay, but it's not good enough. And these are the ways that we describe it, right? And soon we're going to have to change this up, okay? So let's kind of figure out what we want. Well, let's do this. We're going to make this is the series goal, okay? So this is what we want to have by the end of this series. We want to understand this. R mu nu minus 1/2 R G mu nu, which is equal to 8 pi G T mu nu. So we want to take what we know about Newton's gravity. We want to say, okay, now there's going to be certain situations where Newton's gravity starts to fail. Dr. Dirk. So there's going to be a certain situation where Newton's gravity, this thing that we're so used to, this force, you know, with this force coupled together, these potentials that we've seen in classical mechanics and in other, in E&M and stuff like that, where these things are going to fail us. And we need a relativistic form of understanding for these forces and for these potentials, okay? And how do we do that? Well, we're going to need to understand this, okay? So this equation right here, let's talk about that for a second. Let's erase over here. Actually, let's leave that up. Let's leave that up somewhere so we have it for the rest of the day. So our goal, and again, it's R mu nu minus 1/2 R times G mu nu is equal to 8 pi, why is pi so high? Pi G T mu nu, okay? And, so we have, let's talk about that equation for just a second. This is just to inspire you, to get excited about starting to talk about general relativity and switching over from, you know, non-relativistic forces to relativistic forces and relativistic, and let's kind of talk about that a little bit, right? We have the left-hand side of this equation tells us one thing. It's going to tell us the measure, and this is what NC was talking about, which I think is really cool, of curvature of space-time. And the right-hand side is, are you ready for this? This is a measurement of curvature. Basically, how does something curve? How much does it curve? What does it look like when it curves? What shape does it make? All of that is right here. And the right-hand side is the measure of energy and momentum of this matter. Of matter. Now, this is the coolest thing ever. When NC was saying gravity's not a force, this is what he was talking about, right? Newton's gravity, or excuse me, Einstein's gravity. On the left-hand side, we have measure of curvature of a specific space-time. On the right-hand side, we have measure of energy and momentum of matter. Those are the two things. Much like the rest of physics, it seems like Eric doesn't like the cosmological constant and thus chooses to ignore it. That's funny. No, the Einstein's tensor right off the bat. I know, I'm excited. This is what we're doing. This is and Sean Carroll takes the same approach, and I love it. I love just like going right in and being like, this is the goal. This is what we have to unpack. We'll get to the cosmological constant. Does R stand for Ricci? It does. It's the Ricci scalar. Ricci scalar curvature tensor, I think? Hold on, let me look it up real quick. There's the Riemann curvature tensor, and then there's the Ricci scalar something or other. I told you, I really don't know this. Ricci scalar, that's it, Ricci scalar. So we'll have to deal with that in a little bit. There's the Ricci tensor too, but I think you make the Ricci scalar out of the Ricci tensor, if I remember right. It's been a while since I've done this. It's been like almost a year. No, it hasn't been that much, I guess. Okay, so here we have this beautiful thing. We have the measure of curvature of space-time, which is equal to the measure of energy and momentum of matter. I think that's amazing. And we are going to have another goal, too. We're going to have a sub-goal. This one's a little bit beefier, except it may be a little more intuitive, right? And it's what we call the response of matter to space-time curvature, okay? So what are you going to talk about? We're going to talk about the free particles. So something that's free, a free particle just floating around, is always going to move along the path of shortest possible distance. Right? That's just a law of nature, that a particle is going to if it's free, if it's not interacting, if it's not like bound to anything, it's just going to take the shortest possible path. What's UTV? That's the stress energy tensor. Very good, Froggy Watch. Awesome. That's awesome. So the stress energy tensor is basically going to say like, it's basically like how, remember the egg thing that we did where we had like the egg, and I was squeezing the egg. I have a clip of it somewhere. You guys can look at the clip. It was an egg and I squeezed it. And if you take an egg and you squeeze it in the palm of your hand, you can't break it. No matter how much you try, you can't, like it's too difficult to break it. Because the way that it's set up is everywhere along the egg, there's forces that are coming in at every direction, and the way that the interactions happen inside of the shell evens it out all the way across the surface, and it basically cancels. And the way that you can do that is you can write the strain and the stress of the atoms inside of the shell, the molecules inside the shell, and the strain and the stress can be written as a tensor, basically like I think it's a 4x4 tensor. I can't remember. I think it's 4x4 tensor, and it is basically like how something moves when it's under strain and under stress.
Hydrate.
Hydrate, thank you. Oh, it shows up now. Yeah, exactly. It's an energy density, very good, not just energy. Thank you. I love this. You guys like sharing notes and everything. That's awesome. TV describes the energy density in a space. Yes. Excellent. Okay, great. Now, what's this called? This is called the geodesic. The shortest possible... Geodesic. The shortest possible distance, or shortest possible path a particle can take is named a geodesic, and we're going to be doing it a lot. Now, we have a geodesic equation. And this is going to be like one of those things like, remember when we did the path integration, how we were like, we want to do something for a free particle. And then what we're going to do is we're going to say, we know that all particles aren't free. So we're going to adjust that free particle motion, or that free particle interaction, I said. And we're going to say, okay, now it's going to interact. It's going to be subject to some potential. It's going to do something, and we're going to have to change that. Geodesic is a straight line. It's also the shortest straight line that an object can travel, though. The shortest part is very relevant, too. So geodesic equation is basically going to talk about the motion of a particle. And let me give this. The other goal in this series is to help understand what this is. We have a Christoffel symbol here. Sigma. Now this is not the rho that is the mass density. This is just an index. So don't worry, those are not the same thing. This is just an index. They call dummy indices. And that is what they called me in high school. And this is equal to 0. Let's keep moving on. And then we could say that, so this is why we could say that gravity is not merely a force, but a feature of space-time, right? That is exactly what NC was saying, which was excellent. Little what's that called? Foreshadowing of the events is, right now, seriously, is that you can have, that gravity is not merely a force, but it's a feature of space-time. Something about this measure of curvature of space-time is directly related to the measure of how much energy and momentum of matter exists in a certain area, given by, that tensor that we were talking about in chat. Very cool. So the geodesic plays a role like action. Yeah, exactly. In that it's the quantity to be minimized. Yep, very good. And that's what this geodesic equation is going to do for us, I think, if I recall correctly. A lot of this is me trying to remember foreshadowing of stuff that Sean Carroll hasn't talked about yet. But I learned once, and I just don't remember it too well. Okay, so let's keep going. Because now we can start to head back. Okay, so now we laid out the plan. The plan is to understand these two. This is like the least action. This is our gravity. We know that now we're saying that space-time has some sort of special thing about it, where we can relate the curvature of it to how much energy and stuff is in an area or whatnot. The density of it. Very good. But we're still going to go back a little bit too. We have to talk about a couple things first. The Christoffel symbol has entered the chat, yeah. So before we, pre-special relativity, we had 3 dimensions of space and what's called one time parameter, right? We used time before special relativity. It showed up all over the place. And let me kind of show you a picture of what we're talking about here, I hope. Where we have this is going to be a 2-dimensional space and one parameter of time, but you can just imagine scaling this to 3 dimensions of space and 1 dimension of time. There we go. So this is the picture from Sean Carroll's notes that I shared on Discord. This is the stuff that we're allowed to work with on chat, and it's awesome that he's let us do this. Now, we have the 2 dimensions of space, and you can just, like I said, you can imagine 3 dimensions of time, but each space in time, each point, each parameter t, there is a different plane. And that's the way that we've always thought about it pre-special relativity. We just started GR not long ago, Tyrion. Actually, I guess it's been like 20 minutes. But yeah, so each plane is a new time parameter, right? And having it this way gives us a lot of ideas. Like we can have things like simultaneity and stuff like that because it's just a parameter. It doesn't have any intrinsic it doesn't have any intrinsic meaning other than like at this time there's everything on this plane is happening, right? And that's what ultimately gets us in trouble when we want to go to a relativistic point of view. So keep that picture in your mind, and we can write a distance on one of those planes as the following. So we'll have the distance s squared is equal to delta x squared plus delta y squared. That's the Pythagorean theorem, right? So if we had some xy axis, and we call, this our x and this our y, then we could have, oops, there we go. Then we have this being delta x, this being delta y, and this is s. The distance between these 2 points is s, right? And this delta x and delta y is the Pythagorean theorem. You get it, right? Cool. And
that is quite a goal.
Tyrion. Yup. And it's a good goal though. It's a good goal to have. And we're gonna take as long as we need. I mean, like, this is just for our own learning. So if it takes us 3 months, takes us 3 months. If it takes us 2 weeks, it's gonna take a lot longer than 2 weeks. Sorry guys. Okay, now what if we had a different coordinate system, right? Maybe one that's shaped differently. So we could have another one, and we'll say s squared, same s squared, is equal to delta x prime squared plus delta y prime squared. So let's say now that instead of this shape, we have some other coordinate system that's bent like that, okay? And how do we have the same s squared? Well, there's a type of symmetry that we can take advantage of. Let's go back and look at that picture again. And this is the symmetry that we really want right here, right? So we have our original one where our delta x is right here, right? And then we have our delta y right here, and then we have our s, okay? I think he calls it delta s here. It's the same thing. But there's another way we can look at a different coordinate system, one that's tilted or turned. And if you notice that the same delta x, or a new delta x prime, and a new delta y prime can still be combined to give you the same delta s. See how that is? We rotate the coordinate system, and the distance doesn't change. The distance remains the same. And that distance is going to be key to understanding a lot of what we do in general relativity and in special relativity as well. Now, I'm going to go back to the main thing. Excuse me here. So if we look at the diagram, we can see that the distance is unaltered under a rotation. Does anyone know what this is called? Does anyone know what that's called when it's altered under a rotation? But that's not the case for Newtonian physics with space and time. Like if you go back to that picture of the slices, some might say it's invariant. Very good. The parable at the beginning of space-time physics is really good at describing this part. I'll have to look that up. Space-time physics? Yes, but you're right, Froggy. It is invariant under a rotation. Awesome. So that invariance is going to come into play when the action doesn't, or when the distance doesn't change under a certain transformation of these coordinates to new coordinates, then we call that invariance under that transformation. So let's introduce some special relativity definitions before we keep going any farther. So again, if you have these in the notes on Discord, awesome, and you can take a look at them. I'm probably just going to read them and not write them all out because that would take a lot of time. But the first one is space-time. So in space-time, we have a 4-dimensional set with elements labeled by 3D space and 1D time. You might see something like this. So for space-time, we might have a 4-dimensional set of elements, 1 time, and then 3 space. Okay? And then an event is another definition, an individual point in space-time. So we actually have a video on that on YouTube about that type of stuff, which was going to be the homework for next week. I'm going to give you guys homework. It's watch one of my YouTube videos and like and subscribe and comment. That's a joke. And an event is an individual point in space-time. That's it. An individual point in space-time. So we have this 4-dimensional space. A 0-dimensional point is called an event. A world line is a path whose curve is parameterized by a set of 1D events. So you can imagine that picture of planes, right? And any type of line that goes through the planes will have an event every time it hits a point in space, or a point in time, I should say. Okay? That is a world line, that path that the particle is taking. Now, the lines are not the best, the planes are not the best way to think of it. We need light cones, but that's going to be in the YouTube video, is the light cones. Now, with those definitions, we have large consequences. Oh, I got disconnected from my chat. There are large consequences in special relativity for those planes. Basically, we have no notion of simultaneity. If we take advantage, oh, I'm sorry, not the planes, but if we take advantage of these definitions of special relativity, space-time, events, and world lines, then we have...
were chatting about how much we hate you.
Came back to hear something about time. There it is. I only am going to allow group theory conversation. I wish I could have like a, you know how they have like follower-only chat or like emo-only chat? I wish I could turn it into group theory-only chat, so you guys are only allowed to talk in terms of group theory. It's invariant under the transformation of SU2 to SU2. So there's large consequences in special relativity, namely no notions of simultaneity. So now with our space-time coordinates, let's address time. Let's address our new time, okay? So we're going to do a little thought experiment, okay? Thought experiment. Here we go. This is everybody's like favorite thing to do with general relativity. I'm pretty sure you're required to do it at least once. And we're going to get ours out of the way, okay? Because everybody wants to be like Einstein. I want to be like Einstein. What about you guys? Man's smart. So we're going to do a thought experiment, but I'm going to show you with my chalk. So you can imagine having... Oh, don't drop it. Oh, man. That'd be like a cardinal offense. Let's see here. Okay. So you can imagine having a 3 right-angled coordinate system, right? I'm trying, guys. I'm trying. Okay, there we go. Where they have 3 right angles and you get 3 dimensions of space, right? Here we go. Here's 3 dimensions of space. Now, imagine that at every single point, so these go on infinitely long, okay? Right? Infinitely long. And if you take and put a clock, now we're talking about an actual clock, take and put a clock at every single point in that space along those 3 lines, those infinitely long 3 lines, okay? Now we're going to do a little something with that. Where'd my notebook go? Oh, there it is. So at every point in this infinitely long stretching rods, or pieces of chalk, we are going to set a clock. Now we're going to take point, this is going to be point 1, okay? Point 1, it doesn't matter where it is. It's just point 1. I wrote pot. What? So here's point 1. And then over here. Blurry. Oh, you're right. Thank you. I forgot to focus. Focus, Eric. Focus. Man, this guy. Thank you for that. And so starting stream, we have gained 7 new nerds in the Discord. Awesome. I'm glad you guys are enjoying this enough to want to join the Discord. Welcome, friends of the Discord. Okay, so now the goal is going to be to shoot a beam of light from point 1 to point 2, and it has to travel at the speed of light, okay? That's the point of the thought experiment, is we're going to shoot a beam to here, okay? The light is going to leave point 1 at T1, okay? So at T1, light leaves. At T2, light hits point 2. But at point 2, there's a mirror. Okay, it's a nice mirror. It's a pretty mirror. And it's going to reflect the light immediately back to point 1. So at time T1 prime, the light returns. Okay? We can do this mathematically. We can say this is T2 is equal to 1/2 times T1 prime plus T1. Okay? Straightforward math. You can do that, right? It's very, very easy, okay? It takes half the time to get for here than it takes to do the whole trip, okay? Now, what does that mean? Well, that means that this is what we would call an inertial frame of reference. So in this group of reference frames right here, we have a definition for this, and this is the inertial frame of reference. This isn't true in Newtonian physics. Well, there is inertial frames of reference in Newtonian physics, but we have issues with those frames of reference. We can think, though, of, let me see if I can find the page in Hartle where it has some pictures. And the pictures in Hartle basically show a bunch of frames of references, or a bunch of, inertial frames. So here we just have some different frames of reference. Let me draw some of them. We have, a guy in an elevator, and he's sitting in a chair, right? And he's being accelerated by some force, some thrust. And then we have a guy who's in an elevator, and he's spinning. So he's being accelerated to, one of the sides as there's some rotational motion. And then there's a couple pictures of a guy in free fall, right? And in free fall, where he's just sitting there falling, and he's not touching any of the sides, then we can have an inertial frame of reference, right? Because we have, because we can define it as something like this, okay? Where we have the time goes from here, and it's the same distance, and there's nothing weird going on with time. It's exactly what we expected. But we do have a bit of an issue when we're trying to go from one reference frame to another reference frame, using this as an inertial frame, when we're talking about Newtonian physics, okay? We actually don't even have that much left today, guys. Maybe 15 more minutes, okay? And then we'll do questions and everything like that. So Newtonian physics has free particles, which can have, inertial frame of reference. And how do we define that, right? Well, we define it in the following way, right? We can define a parameter t. Remember, this is Newtonian physics. Okay, so parameter t, and this is the Newtonian one. This is the one we don't want. Do not want. Okay, we don't want this one. And how is this figured out? Well, it's figured out the following way. D squared x divided by t dt squared is equal to 0. What does that mean? Well, remember, force is equal to mass times the acceleration. Acceleration can also be written as d2x over dt squared. And for the mathematicians in chat, we can move that dt around however we want. Like, I could put it up here and it's fine. You can do whatever you want with the dt. It's fair game. And if this is equal to 0, so if this is 0, then our force is equal to 0, and we get a particle without force. It's a free particle. This is certainly the definition of a free particle, right? It's floating around, and we could talk about a particle in this inertial frame of reference with some parameter t that we can define this way. Not a big deal, right? In Newtonian physics, it's not a big deal. But there's also a new inertial frame of reference that says for any of these new t primes, we can take the old t and add some constant to it. But this gives us, again, back to that notion of simultaneity. And simultaneity is something we don't want in in Einstein's relativity. We don't want simultaneity. We know that that can't be right, because then we could just say that, you know, that they're all equal at some point or whatever. And that gives us a bunch of issues, okay? So instead, Sean Carroll lays it out this way. He says space is defined by t equals some constant. So this is what we don't want. Let's make sure we know that this is what we don't want. Okay, and this is what we do want, according to Sean Carroll, and I believe him. I hope you guys do too. And we're going to find out together as we keep learning this, that we want some space that's defined by having t equal to some constant and t prime also equal to some constant. Oh, I'm sorry. Hold on. Space defined. Okay, so space defined by this, there we go, will be different than spaces with this. Let's rewrite it. Spaces defined by t prime equal to constant. There's in Newtonian physics, there's only one type of space, right? It's the space where time just behaves the same way in everything, right? It's not, time is not a coordinate, it's a parameter. Space exists on x, y, and z inside, and every t ticks off as some just parameter. You can't do anything with it, it's just a parameter. But now, what Einstein says is no, t is actually going to be part of the way that space is shaped. Like, t is going to have a significant role in the way that space is actually shaped. Okay, so now we have to say, okay, so now we know that, like, this is what we want. We want space that's defined differently at every version of t, okay? It's going to be part of space. Let's unpack that more. Not Phantoms, welcome to the channel. Thank you for the follow. If you have any questions, if anybody has any questions, exclamation mark ask and then your question. So what motivates involves negative coefficient? I never understood that. It has to do with where it comes into the light cone. Boring math professor. I don't know of like any foundational reason other than the light cone. Like, so in we have three different types of world lines. We have time-like, space-like, and light-like. And in order to get time-like to be causal dependent, like each event can happen causally inside of the light cone, then we need to have that negative sign on the metric. And then some cool things happen, but that's also all explained in the YouTube video if anybody else is interested. But I think that should do it, and we'll get to it next week, actually. There's also a lot of problems you get into when you have a positive, when you have four positives. But Xvention would know those. I don't know those off the top of my head what the problems are. But I do know that causally dependence relies on that original negative. Now, let's talk about those spaces. So we're going to define a new integral, or not integral, interval, mind you. And this new interval is going to be made up of space. We're about to see our first tensors, if you guys are all excited. I know you're excited. We're almost done, too. Delta s squared is equal to negative, and then this is going to be where we first see this. And this is going to be kind of like the theme. And I'm sure everybody's seen this a lot and is like, I always wondered what this was. But we have c, the speed of light, negative, excuse me, and then times the quantity of c times delta t squared, plus delta x squared, plus delta y squared, plus delta z squared. And this follows from the same thing we saw before with the little triangle and the two delta x and y's, right? And they make some sort of hypotenuse or Euclidean, whatever, mamma jamma, who cares, right? And so this is just to define a length of space, okay, a distance. Should we take care of the elephant in the room by making it equal to 1? Oh, you will. You will. Important role of C is okay, so this is the important role of C, okay, before we get rid of it. The important role of C is that it's a fixed velocity, and it exists such that, and this is what Sean Carroll says, it's important. He is the expert. I'm not the expert. He is the expert. The space-time interval is invariant under changes of inertial coordinates. So that's the relevance of C. C is a velocity. It takes, a unit of time and makes it a unit of space, which is why we need a velocity here, to take the unit of time and make it a unit of space so that all the units match. But this C is special because it goes back into that thought experiment, right? That thought experiment about shooting the light from point 1 to point 2 and then have it coming back to point 1, right? That relied on the speed of light in order to make some sort of inertial frame of reference, right? And now, as we change the distances, we do the whole, we had a coordinate system here and we changed it, right? And we found that the space was the same under a rotation. If we want inertial references to be invariant under those rotations, we need C. C is very important for that. Okay, and now, so let's talk about some sort of transformation that happens. Say we just do like a rotation, right? This is going to be the new one, okay? The new rotation, negative C delta t prime squared plus delta x prime squared plus delta y prime squared plus delta z prime squared. Notice how this c is a constant, it's the speed of light. It doesn't change, but this s is the same thing as well. And now we're saying that under some rotation of coordinates, the same rotation we did before, then we know that there is invariance in that rotation. And the fact of the matter is that's mostly because of C and what role it plays in the inertial frame of reference, okay? Now a space that exists under these invariant transforms is called Minkowski space. This is flat space-time. Minkowski space. This is, and ready for some big jargon, Minkowski space. 4D manifold. And we'll introduce this soon. I'm just going to say it's a 4D manifold. If you know what that means, great. If you don't, hang on to that. It is the space in which this is invariant transformation happens, right? ds is the same, follows the same thing, except now we're in 4 dimensions. Okay. Are you ready for the juicy? Are you ready for the juicy? Let's introduce some tensor stuff. So firstly, we're going to start with coordinates, okay? And these are our vectors, not tensors. These are firstly our vectors, our 4 vectors. And then we're going to introduce the tensor after that. But the 4 vectors, I guess you could say a 4 vector would be a tensor rank 1, right? Is that correct? Someone correct me. And for our specific cases, we're going to have Greek letters for the 4 vector. The 4 vector runs over 0 to 3, and it exists as the following way. X mu is x sub 0 is equal to ct. So it's right here. This is the first, or excuse me, this one is the first part of the vector. x1 is the second thing in the vector, delta x. x2 is equal to delta y. x3 is equal to delta z. Okay? Vectors can be tensors. All this physics is making me tensor. And tensors can be vectors because they form a special vector space. Cool. Tensor rank 1 is vector. Great. That's what I thought. Okay, and then x with Latin letters is going to be a 3 vector. 3 vectors. So we're going to go 1 through 3. And they're the same way. So that means x1 is equal to delta x. This is in case we want something with just space and we don't want to bother with time, which will be relevant. But not today, I don't think. No, in fact, no, not today. So here we have a 3 vector and a 4 vector. You can think of them as tensors rank 1. And now, if you're a sub, make sure you put in chat, we get to set C equal to 1. We will now be using natural units. Let's do it. For the most part, we are going to be using 1. So set E equal to 1. Get those natural units into chat. Love to see them. And then let's... Is a rank 1 tensor a tangent vector or a cotangent vector? I have no idea. No clue. I think it's a tangent vector. Not 100% sure though. Let's go with tangent. I'll look that up. I'll have to look that up. Let's look that up. Okay, so let's introduce a rank 2 tensor. All right, so let's introduce our first. Now we're going to finish up. This is the end. We have a rank 2 tensor, a 4x4 matrix, and this is what we are going to call our first metric. Okay, here's some mu and nu for you, and this is our 4x4 vector. And then we're going to show you how this notation makes this tensor very helpful. Okay? So now we can rewrite our metric. I'm going to write it right here. You see that long thing that I had all the way across here? Now I'm just going to rewrite it here as the following. Delta S squared is equal to eta mu nu, delta x mu, delta x nu. And that's it. Now, this looks a little daunting to you, right? But it's not. Don't panic. We have what's called the summation convention, where we're going to use this. Basically means that we're going to use the upper and lower indices to sum over every single point in the space. So mu and nu are pieces of this matrix. So we have, like, if we want mu to be this way and nu to be this way, I think that's how that works. They're equal, so I guess it doesn't matter for this case, but I'm pretty sure mu goes down and nu goes that way. Someone correct me if that's wrong. But it's basically, this is like 1, 1. This would be 1, 2, 1, 3, 1, 4. And then, 2, 1, 2, 2, 2, 3, 2, 4. But notice how the only areas, the only values, the only elements of this matrix that are not 0 are on the diagonal. So 3, 3. And 4, 4. Wow. So those are the ones that are not on the diagonal, or those are the ones that are on the diagonal. Excuse me. So we're going to sum over all of these, but we know that any combination of mu nu that is not the same is equal to 0. So let's try to write this down. So we have delta S squared, and it's just going to be a little tensor analysis. We're going to try to plug in the numbers here. The first one is going to be 1, 1. So we have 1, 1. So what's the value for eta at 1, 1? It's -1. And then we have delta x to the 1. Oh, these have to start with 0. Who's correcting me? Sorry. These are supposed to start with 0. My bad, my bad, my bad. Let's just erase them so we don't get confused. Ho-ho. Or else it doesn't make any sense. Why does it not make any sense? Well, it's Greek letters. I said Greek letters have to run from 0 to 3. So this is 0, 0, 1, 1, 2, 2, and then 3, 3. So then we have delta x 0, delta x 0. And then we have to sum all of the terms. So then next we would have 0, 1, but for eta we get 0, so that goes away. 0, 2, but again, eta is 0, so that goes away. And we'll go all the way till we get 1, 1. So what do we get at 1, 1? Well, we get 1 for the value of eta. And then delta x to the 1, and then delta x to the 1 plus. Same thing, you get to 2, 2, and you have delta x, well, 1 times delta x to the 2, delta x to the 2, plus the last one, which is 1 times delta x to the 3, delta x to the 3. What are these values? Well, if we go back to the previous Blackboard slide, then what you get is minus t delta t squared, the c is equal to 1, plus delta x squared, plus delta y squared, plus delta z squared. And we have reconstructed our original delta s squared, all by using this easy notation. Okay, so there is a lot of benefit of having this notation. And this is it for today. We introduced a first tensor. We have begun our tensor analysis. Next week we're going to do a lot more of this, but this is the goal. We want to use this little tiny notation with knowing what this metric is for each shape of space, so that we can figure out if we take a shape of space, okay? So this metric is really what's telling you what space looks like, okay? If we take a shape of space, right, and we get the metric for that shape, and then we say, I want to know what a line distance is, so we'll call this delta S. I want to know what this is on the surface of that shape, okay, or on any part. Well, yeah, let's do surface. Well, let's do any part of the shape. Any part of the shape, let's do this, delta S. Then we know that all we have to do is take the metric of that shape, and then take these two values for our coordinate system, and then we can figure out what this value of delta S looks like on that specific shape, okay? So now we're starting to see how this is going to, go about the next few weeks. So this eta is a tensor of what rank? This is a rank 2 tensor. Try and learn the terrible physics language for this. Absolutely. Yes. Rank 2 tensor for this. I love it. I love it. Any questions about the stuff today? I just think it's so cool. I think this stuff is so cool.